I was walking my dog this morning, trying to avoid eye contact with the neighbor who's always washing his car at 6 a.m., and I found myself just staring up at the roof lines.
Hmm.
And I realized something. To me, and I think to most people, a chimney has always been, well, the definition of a static object.
Right. It's a pile of bricks.
It's a pile of bricks, it's heavy, it's solid, it just sits there. It feels like the most immovable thing on the entire house.
That's the perception, right? It's the visual anchor of the home. I mean, we use phrases like solid as a brick wall for a reason.
Exactly. But then I started digging into the source material for today's deep dive, and my entire worldview on masonry kind of crumbled, pun absolutely intended.
Okay.
Because apparently a chimney isn't static at all.
Not even close, no.
It's actually a dynamic, moving machine.
You know, that is the perfect word for it. It is a machine. It expands, it contracts, it breathes. It's constantly battling two very powerful elemental enemies at the exact same time.
Which are
Extreme heat from the inside and water from the outside.
always. And when it's built wrong, which, spoiler alert, it seems to be the default for a lot of builders, it literally destroys itself from the inside out.
Often silently, too. You don't know what's happening until you see the cracks on the outside, and by then, the internal damage is usually catastrophic.
So today, we are diving deep into Chapter 4 of the book Sit to Success. The author is Ray Gessner, and I noticed the PE after his name immediately.
Professional engineer. And that's a crucial distinction. Ray isn't just a mason sharing, trade secrets. He's an engineer applying hard physics and thermodynamics to what most people think is just stacking rocks.
Right.
It's a different level of analysis.
Our mission today is to decode the engineering secrets of chimney construction.
Into it.
Okay, let's start at the very top. The absolute first line of defense. The chimney cap and the spark arrestor.
The lid. The little hat on top.
Right. Now, looking at this, I think the average homeowner assumes this is just a rain hat. You go to the hardware store, you buy a metal box, pop it on, and you're done. But Gessner goes into some serious math here.
Oh, yeah?
It's not just about covering the hole.
No, it's about flow dynamics.
Yes.
And it starts with a concept called net-free area.
Net-free area. Okay, let's unpack this because this feels like the first place where DIYers and even some pros get it completely wrong.
It is. So imagine you have a chimney flue. That's the clay pipe the smoke comes out of. Let's say it's a standard square flue. That pipe has a specific cross-sectional area.
Yeah.
That is your baseline for flow. Now, you're putting a cap with a mesh screen over it. That mesh is made of metal wire.
Right.
Even though mesh looks open, every single strand of that wire takes up physical space. It blocks a percentage of the air. Plus, the air has to hit that cap, turn 90 degrees, and then squeeze through the holes. All of that creates drag.
It creates resistance.
Exactly. It's aerodynamic resistance. If you just slapped a flat piece of mesh directly over the opening that was the exact same size as the flue, you are significantly restricting the draft.
So you're choking it.
You are. It's like trying to run a marathon while breathing through a straw that someone has partially pinched shut.
And the result of that is a smoky living room, or is it more subtle?
Well, it can be a smoky living room for sure, but more often it's just a sluggish draft. The fire burns poorly, it's hard to get started, and you get rapid soot buildup because the gas velocity drops, the smoke is moving too slow.
So what's the golden rule here? How do you avoid choking your own chimney?
The rule, the code, is that the net-free area of the cap or a spark arrestor must be at least 4 times the cross-sectional area of the flue it serves.
Wait. 4 times?
4 times.
Oh.
400%.
That seems massive. That sounds like overkill.
It sounds huge, doesn't it?
Yeah.
But you need that 400% capacity to compensate for the wire thickness, the turbulence from turning the corner, all of it. You need the air to feel like there is zero obstacle. The goal is to make the cap functionally invisible to the airflow.
So if I have say a 12 by 12 inch flue, which is 144 square inches, I can't just have a 12 by 12 inch area of mesh. I need, almost 600 square inches of open mesh? That's a massive cage.
Precisely. That's why proper caps look so big and airy. If the cap looks tidy and flush with the pipe, it's probably choking your fireplace.
That is a great rule of thumb. Now, within that cap, we have the mesh itself, the spark arrestor. And this leads us to what I'm calling the mesh paradox.
It is a bit of a paradox, yeah. You have 2 competing goals here, and they're both about safety.
Right.
Goal A, stop burning embers from flying out and setting your roof or your neighbor's roof on fire.
Right.
Goal B, let the thick, particulate-heavy smoke escape freely.
So if you prioritize safety too much with a superfine mesh, you block the smoke.
You block the smoke,
But if you prioritize flow with a big open mesh, you burn down the neighborhood.
Exactly. So the code has carved out a very specific Goldilocks zone for the size of the holes in the mesh. It's incredibly precise.
Okay, walk us through the measurements. This is fascinating.
The mesh must block spheres that are half an inch in diameter.
Okay, so a half-inch marble cannot get out. That's your burning ember.
Right. That stops the dangerous embers. But it must allow a sphere measuring 3/8 of an inch to pass through.
Wait, okay, let me do the math on that. Half an inch is 4/8. So you have to block 4/8, but past 3/8, you are working with a tolerance window of 1/8 of an inch.
That is the window. It's incredibly tight. If the holes are too big, dangerous sparks escape.
Yeah.
If the holes are too small, like if someone uses, window screen or even chicken wire, which can be too small or irregular,
It just clogs up.
it clogs up like a lint trap, but with flammable creosote.
Oh, that's bad.
It clogs almost instantly. And then you have a total blockage, which sends carbon monoxide back into the house. So the industry standard to hit this needle-eye target is usually a 34-inch expanded metal pattern. It's really the only thing that balances the flow and the safety perfectly.
So note to self, do not improvise on the mesh. Just buy the right thing.
Never improvise on the mesh. And there's one more non-negotiable on caps the Gessner highlights, and that is removability.
This seems obvious, but I'm guessing it's not.
You would be shocked. I've seen caps that were mortared or even epoxied permanently in place by the mason who built the chimney.
Which means?
Which means you can never clean it. A chimney sweep needs to get a brush all the way down that flue every year. If the cap is cemented on, that chimney is a time bomb. It violates code because it effectively prevents maintenance. Caps must be bolted or clamped. Removable.
Okay, before we move down the chimney, I want to talk about multi-flue caps. This is when you have one giant metal lid covering, say, a fireplace flue and a furnace flue right next to each other.
The hood style. Yeah, very common.
There's a height rule here that Ray Gessner highlights, and it involves some geometry that I think a lot of installers miss.
This is a major failure point. The rule, per NFPA 211, is about how high that lid sits above the actual clay pipes.
Okay.
The vertical distance from the flue top to the cap lid must equal the lesser dimension of the flue opening.
Can you give us a real-world example? What does that mean?
Sure. Let's say you have two flues, and they're both standard 13 inches by 13 inches. The lesser dimension is, well, it's 13 inches.
Right.
That means the metal lid of the cap must be floating at least 13 inches above the top of the clay tile.
13 inches is pretty high. I feel like I usually see them sitting much lower, maybe 6 or 8 inches for a low-profile look.
You absolutely do, and those are installed incorrectly, every single one.
So why does the height matter so much? What's the risk of having it too low?
It's all about turbulence and heat. If that lid is too low, the smoke comes up, hits the lid, and has nowhere to go. It swirls around, that's the turbulence,
Yeah.
and can actually get pushed back down the other flue.
You're kidding.
Yeah.
So you light a fire in the living room and smoke comes out of the furnace in the basement.
It happens all the time.
Right.
That's cross-drafting.
Mm.
And secondly, there's heat buildup. If that hot gas can't escape sideways fast enough because the lid is too low, the heat just concentrates under that hood. It can warp the metal, ruining the cap, or even overheat the concrete crown below it.
So the low-profile look is actually a functional disaster.
Physics creates the profile, not the architect. That's the rule.
Okay, let's move down an inch or two. We need to talk about the flue tile extension. This is the part of the clay liner that actually sticks up out of the masonry on top.
The little orange clay pipe you see poking out the top.
Right. Ray describes this as another Goldilocks situation. It can't be too short and it can't be too tall.
Correct. The standard is very, very specific. At least 2 inches, but no more than 4 inches.
Let's unpack the at least 2 inches part first. Why not have it flush? Why not just have the pipe end right where the concrete ends? Seems cleaner.
2 main reasons. First, water management. If the tile is flush with the concrete crown, any water that lands on the crown can drain directly down into the flue. It's a perfect funnel effect. By having it stick up 2 inches, you create a curb, a dam. Water hits the crown and flows away, not in.
That makes perfect sense. And the second reason...
Attachment. Remember we just talked about bolting on that chimney cap? You need physical surface area to clamp or bolt that cap onto. If you only have half an inch of tile exposed, that cap is going to fly off in the first windstorm. You need that 2 inches of grip.
Okay, so that's the minimum. But why is there a maximum? Why can't I have a foot of flue tile sticking up? I've seen that.
Oh, you see it all the time. And it's a huge problem because of thermodynamics and structural leverage. This is where people get into trouble.
Go on.
Okay, think about the winter. It's freezing outside, wind is blowing. If you have 12 inches of clay tile exposed to that wind, that clay gets very, very cold. Now, your furnace or fireplace sends hot gas up the chimney. That gas is maybe 400, 500 degrees. It hits that super-cooled section of tile right at the top.
And when hot gas hits a cold surface?
Condensation. The gas cools down rapidly. Cool gas moves slower, so you lose your draft right to the finish line. But worse, the chemicals in the smoke, the umber hydrocarbons, condense into liquid. That liquid is creosote.
So a tall exposed liner basically becomes a creosote factory at the very top of your chimney.
Exactly. You're creating a plug of flammable gunk right at the exit. And then there's the structural problem. Think about the wind again. A tall tile requires a tall cap.
Right.
A tall cap acts like a sail. In a 50-mile-per-hour wind, the leverage that sail exerts on that exposed clay tile is immense. It can crack the crown at the base or even snap the tile off completely.
So 2 to 4 inches, that is the safe zone, the only zone.
That's the only zone you should be in.
All right, let's talk about the crown. Now, before I read chapter 4, if you asked me what a chimney crown was, I would have said, the cement part on top.
And you're not alone. Unfortunately, a lot of masons treat it that way too. They just smear some leftover mortar on top of the bricks, taper it off with a trowel, and call it a day.
Ray Gessner seems to really hate that.
Because it's not a crown. That is a wash, a mortar wash. And mortar's not waterproof, it's a sponge. It absorbs water, freezes, cracks, and fails within a few years.
Okay.
According to our source, specifically the ASTM-C 1283 standard, the crown is actually a structural concrete roof for the chimney stack.
A roof within a roof. I like that.
Precisely. It protects the entire masonry column below it from water intrusion. It is the most important weatherproofing element.
So let's walk through the specs of a proper ASTM-C 1283 crown. First up, and this seems huge, the overhang.
This is non-negotiable. The concrete needs to project 2 inches past the brick wall of the chimney on all sides. Think of it like the brim of a hat.
And what happens if you don't have the hat brim? If it's just flush?
If the crown is flush with the wall, water runs off the top and slides directly down the face of the bricks every time it rains. Over time, that water saturates the brick. When it freezes in the winter, the water expands and pops the faces off the bricks. That's called spalling.
I've seen that, the flaking bricks.
That's usually a crown problem.
Yeah.
It also washes out the mortar joints, leading to structural instability over time.
So the overhang forces the water to drip off away from the wall.
Well, gravity tries to make water drip, but water has surface tension. It's sticky. It likes to curl back underneath things.
Right.
That's why the second requirement exists, the drip slot.
The drip slot. This sounds like spycraft, but it's actually just physics.
It's simple but brilliant. On the underside of that 2-inch overhang, about 1.5 inches out from the brick face, you cast a groove into the concrete as you're forming it.
What does the groove do?
It breaks the surface tension. As the water curls back under the ledge trying to get back to the bricks, it hits that slot. It can't bridge the gap. Gravity wins, and the water is forced to drop straight down to the roof, completely clearing the chimney wall.
It's amazing how much engineering goes into just moving a drop of rainwater 3 inches to the left.
Water is the persistent enemy. It's relentless. You have to outsmart it.
The source also mentions reinforcement. We aren't just pouring concrete here, we're reinforcing it.
Absolutely. Minimum 2 inches thick at the outer edge, and it must contain 12-inch wire mesh. Concrete shrinks as it cures, and it expands and contracts with the weather. Without that mesh, you are guaranteed to get hairline cracks.
And hairline cracks let in water, which freezes and expands.
And suddenly, your beautiful crown is in 3 pieces. The mesh holds it all together during those thermal cycles. It provides the tensile strength that concrete lacks.
Speaking of shedding water, we can't have a flat crown, right? No puddles.
Never. A flat crown is a code violation. ASTM-C 1283 requires a slope of at least 10 degrees downward from the flue liner to the outer edge. No bird baths on top of the chimney. Puddles lead to ice, and ice destroys concrete.
Now, what if I don't have a masonry chimney? What if I have one of those wood chase structures with siding on it?
You still need a crown, but it's usually metal. And the rule there is that it must overlap the sides by at least 4 inches and have a flared drip edge. Same exact principle, different material.
Get the water away from the walls.
Get the water away from the walls.
Okay, so we've built the perfect crown. It's reinforced, it slopes, it has an overhang with a drip slot. But now we come to what I think is the most dramatic part of this deep dive, the battle between the crown and the flue liner.
This is the core conflict. This is where the machine aspect really kicks in.
Section 4 calls out the bond break. It sounds like a bad breakup, but apparently it's essential for a healthy chimney.
It is the single most common and most catastrophic mistake in chimney construction, bar none.
Explain the setup for us. What is the mistake?
Okay, you have the clay flue liner inside, that's your hot exhaust pipe, and you have the massive concrete crown on top, that's your heavy roof. The mistake is pouring the concrete directly against the clay tile, bonding them together into one solid, rigid unit.
Why is that a mistake? It seems like it would make it strong, you know, tie everything together.
It makes it rigid. And rigidity is fatal here because of one thing: thermal expansion.
Let's talk numbers. Why is thermal expansion such a big deal here? It sounds like a micromeasurement.
Vitrified clay expands when it gets hot. The coefficient is about 4 to 5 times 10 to the negative 6 inches per inch per degree Fahrenheit.
Okay, that sounds like a tiny, tiny number, 10 to the negative 6.
It is tiny per inch. But you have a liner that might be 20 or 30 feet long. That's 360 inches. And you are heating it from maybe 0 degrees in the winter to potentially 1,000 degrees in a chimney fire, or even 400 to 500 degrees in normal operation. That expansion adds up to significant movement. A quarter inch, half an inch.
So the liner gets physically longer.
It gets longer. Now, the liner sits on the smoke chamber at the bottom of the chimney. It's heavy. It's fixed at the bottom. So when it expands, it has only one direction to go.
Yeah.
Up. It's like a piston pushing upwards. A slow, silent, unstoppable hydraulic ram. Now, imagine you've glued a heavy concrete cap to the top of that piston. The piston pushes up, but the cap is heavy and it's bonded to the bricks. Who wins?
Something has to break.
Something always breaks. Ray Gessner outlines 4 specific failure modes. Let's walk through them because they are terrifyingly common. Failure mode 1, crushed joints.
What happens there?
The liner tries to move up, but the bonded crown holds it down. The source has to go somewhere, so it turns inward. It compresses the liner sections, crushing the mortar joints between the tiles.
So the pipe itself starts to collapse from the inside.
Yes. You lose the seal between tiles, which means hot gas can escape. Failure mode 2, the cracked crown. This is probably the most common one you'll see. The liner is stronger than the unreinforced concrete. It just pushes up and physically snaps the crown in half.
Which lets water in, which we just spent 10 minutes trying to prevent.
The irony, right, correct. Failure mode 3 is my favorite for sheer destructiveness. The lift, or as he calls it, telescoping.
This is the one that sounded scary, telescoping.
This is when the bond between the liner and the crown is so strong that the expanding liner lifts the entire crown and the top few courses of brick right off the chimney.
Wait, it physically lifts the masonry.
It lifts the roof of the chimney. You'll see these distinct horizontal cracks in the brickwork a few courses down from the top. It literally jacks up the top of the house.
That's unbelievable.
And then debris and soot fall into that new crack. When the liner cools and shrinks, the crown can't settle back down because it's resting on the debris.
So the chimney literally grows taller over time.
It grows taller and it cracks itself apart cycle after cycle. It's devastating.
And failure mode 4.
Liner deterioration. Clay is very strong in compression, but it's brittle. If you restrain it while it's trying to expand, it can chip or spall flakes pop off the inside, weakening the liner.
Now, there's this detective trick mentioned in the source called the telltale gap. If I'm looking at a chimney that isn't currently being used, how do I know this is happening?
This is fascinating. So imagine this cycle. The fire heats the liner, it expands up, cracking the crown or lifting it. Then the fire goes out. The liner cools down and shrinks back to its original length.
But the crown doesn't settle back down with it.
Exactly. The crown often gets stuck. The friction from the crack or the debris we mentioned holds the crown up, and it holds that top flue tile up with it. So when the rest of the liner shrinks back down, the top tile stays suspended.
What does that look like?
You'll see a visible vertical gap between the top flue tile and the one below it.
A gap in the exhaust pipe.
A gap in the exhaust pipe, which means hot gas and sparks can now escape into the chimney structure itself, right next to the wood framing of your house. It's a massive safety failure.
And there's one more sneaky failure here that he mentions, buckling.
The silent killer. Imagine holding a plastic ruler vertically on a desk. You press down on the top, what happens?
It bows out to the side.
That's buckling. If the liner is stuck at the bottom by the fireplace and stuck at the top by a bonded crown, it behaves like a loaded column. It has to go somewhere, so it bows sideways.
But it's inside a brick shaft. Where can it go?
It only moves a tiny bit, maybe a millimeter. But it does it every time you light a fire, for years. Over time, the tiles shift. They become offset.
So you get jagged steps inside your chimney.
Yes, and those ridges catch soot and creosote and they create turbulence that ruins the draft. It compromises the whole system from the inside where you can't see it.
So what is the solution? How do we stop this unstoppable piston from destroying the house?
You simply let it move. You install a bond brake.
It sounds so simple.
It is. It's shockingly simple. You wrap the top of the liner in a compressible material, like a foam or fiberglass wrap, before you pour the crown. Or you leave a small gap and fill it with a flexible high-temp sealant. The liner needs to be able to slide up through the crown like a telescope without grabbing it.
It's amazing. The solution isn't making it stronger. It's giving it space. It's building in weakness almost.